This is part 3 of the lecture on non-constant acceleration. Here's how we can summarize where we are thus far once we understand the basics of how you calculate the derivative of a polynomial and the integral of a polynomial. We basically have two reverse processes, and here's how you can summarize those processes. Position, velocity, and acceleration. Let's say that we know what the position of an object is as a function of time. In order to find the velocity as a function of time, we would have to take a derivative. But then once we have the velocity as a function of time, in order to find the acceleration as a function of time, recall that acceleration is the derivative of velocity with respect to time, we would have to take another derivative. Like so. But integration, recall, is the reverse of differentiation. So then therefore, if we already know what the acceleration is as a function of time, in order to find the velocity as a function of time, we would have to integrate. And then integrate one more time to go from velocity to position. So the processes of differentiation and integration are reverses of each other, and you can understand the reversal of those properties with a simple graph such as this. So now we're going to apply the techniques of calculus to simple situations involving one-dimensional motion with non-constant acceleration. Here's how I'm going to begin, however. I'm going to jump back to the situations involving constant acceleration. If you recall, for constant acceleration, I used algebra to derive the kinematics equations. Now what I'm going to do instead is use calculus to derive those same expressions. So let me do that first before I take you through a couple of simple examples involving non-constant acceleration. Okay, so here's how we derive the kinematics equations for constant acceleration. We begin with the definition of instantaneous acceleration. Instantaneous acceleration is the derivative of velocity with respect to time. The first step of this process is actually algebraic. What I'm going to do is take the time interval dt and move it to the other side of the expression. Like so. And now here's what this equation is describing. The easiest way to understand this is to actually draw out a graph of the acceleration as a function of time. Okay, now for constant acceleration, of course, the graph would be a horizontal line. Like so. And then what we're doing here on the left-hand side of the expression is we're taking a look at a moment in time, an instant in time, for example, say, right here, like so. And notice what the left-hand side here is describing. What the left-hand side is describing is it's literally describing the area of this line. This line has an infinitesimally small width dt, and it has a height associated with it, which is equal to the value of the acceleration here, which is constant. That's the left-hand side of this expression. However, it's also equal to the infinitesimal change in velocity over this infinitesimally small amount of time. In order to go from this infinitesimal description to a broad time interval, what we then have to do is integrate. Now we're going to integrate this function over a broad time interval between times 0 and some time t. Okay, let me indicate that here on this graph, by the way, in the following manner. So now let's say that right here is time 0, and then right here is some time t. And then what we're going to do is we're going to find the area underneath this curve. We're going to find the area underneath this curve by integrating this expression. When we integrate this expression, we integrate both sides of it. So on the left-hand side of the expression, we're integrating over the variable t. We start the clock at t equals 0, and we stop the clock at some value like so. But now on the right-hand side, we're integrating over the velocity v. The lower limit of integration is the value of the velocity at times t is equal to 0. That's the initial velocity, v naught. And then the upper limit of integration, that's equal to the velocity at time t, that's the final velocity v, like so. And now let's take a look at the two integrals that we have here. Let's actually begin with the right-hand integral first. Okay, here's how we're going to think of the right-hand side. First of all, the integrand itself is the number 1, which I've not written here. In terms of the variable v, however, think of the number 1 as v to the 0th power, like so. And now if you think of it like this, now we could use the rules for integrating polynomials easily to evaluate this integral. So here's then what we do. We take the value of the exponent and we increase it by 1, and then we divide by that new exponent, and then we evaluate this antiderivative between the initial value of v0 and the final value of v. So take the final value of v and plug it into the function, and you just end up with the final velocity v. Then you subtract from that what happens when you take the initial velocity v0 and plug that into the function, and that gives you v0 like so. So notice that the right-hand side of the expression is just the change in velocity, v minus v0. It always will be. I'm just showing it here explicitly in this example. And now let's take a look at the left-hand side. Okay, now on the left-hand side, the a, remember, is a constant for constant acceleration. So what I'm going to do is actually pull it out of the integral like so, as we say. And then think of right here another number 1, which I've not written. In terms of the variable t, this number 1 that I've not written, think of that as t to the 0th, like so. And then we evaluate this between 0 and t. Okay, and then we just use the rule for integrating a polynomial. Take the value of the exponent and increase it by 1, and then divide by the new value of the exponent. And then we evaluate this between 0 and t. So we then take the upper limit of integration and plug that into the function first, and then take the lower limit of integration and plug that into the function second and subtract, and this ends up being at, like so. So notice that the left-hand side of the expression is the area of this rectangle that I've drawn here on this graph. However, the area underneath the curve on a graph of acceleration as a function of time is also equal to the change in velocity. Once again, integration is the reverse of differentiation. So if you differentiate velocity with respect to time, you get acceleration. If you do the reverse process, if you integrate acceleration, you then get velocity. And now let's go ahead and derive our first kinematics expression by moving the v0 here to the other side. And when we do, we end up with this, like so. And there's the first of our two kinematics equations. And now we basically have to continue this process. We now have to integrate this quantity here to go from velocity to position. Here's then how we do that. Let's keep this in mind. We're going to use this expression here in just a few moments. But for now, remember that velocity is the derivative of position with respect to time. Okay, the first step is algebraic. We take the infinitesimal amount of time and move it here to the left-hand side of the expression, like so. And now in terms of a graph, here's what's being described. Here's a graph of velocity with respect to time, and let me just draw a line like so, where we have here an initial velocity v0 and the slope of the line is the acceleration a. Let's take a look at an infinitesimally small amount of time right here, dt. Notice that the left-hand side of the expression is the area of that line. It's the width, dt, which is infinitesimally small, multiplied by the height, which is the value of the velocity here at this moment in time. But the area of that line is also equal to the infinitesimal change in position over this instant in time. What we want to do once again is integrate. We want to broaden this over a time interval like so. So now let's go from time 0 to time t. And when we integrate this quantity, we're then going to be finding this area here underneath the curve. Here's then how that's done. So on the left-hand side of the expression, we're going to be integrating over time. We'll start the clock at time 0 and stop the clock at time t. And then on the right-hand side of the expression, we're integrating here over position. Now the lower limit of integration is the value of the position at time 0. That's the initial position, x naught. The upper limit of integration is the value of the position at time t. That's the final position, x, like so. And now let's take a look at the right-hand side of the expression first. Okay, once again, the integrand right here is the number 1, which is not drawn. But in terms of the variable x, think of the number 1 that's there as x to the 0th power, like so. And then using this, we can now use the rule for integrating a polynomial. So take the value of the exponent and increase it by 1, divide by that new exponent, and then evaluate between x naught and x. Plug the upper limit of integration into the function first, like so. Subtract them with the lower limit of integration plugged into the function second, like so. And you just end up with the change in position. That's the right-hand side of the expression, like so. It always will be. The right-hand side of this expression always will be the change in position. I'm just showing it explicitly here in this example. And then we've got the left-hand side of the expression. Okay, now, on the left-hand side of the expression, keep in mind that the velocity here is this quantity here. It's this quantity here as a function of time. So let's go ahead and plug this guy here as the integrand then of this integral. Here's how I'm going to write it. Like so. Now this right here is just the initial velocity v naught, but in terms of the variable t, think of it as v naught times t to the 0th, like so. T to the 0th is 1 anyway, so we can then use the rule for integrating a polynomial. And then we've got this quantity right here. Notice that I've isolated everything here in parentheses because I'm going to be adding the two terms together. That's perfectly fine, and we just find the antiderivative of each term as we go. So that then gives us the following. So for the first term, take the value of the exponent and increase it by 1, and then divide by the new exponent. Do the same thing in the second term. Take the value of the exponent here and increase it by 1, and then divide by the new exponent. And then this whole thing here in parentheses is the antiderivative, which we then evaluate between 0 and t. So take the t and plug it into the function first, and when you do, you basically just get the function. Like so. And then take the 0 and plug it into the function here and subtract, and it just ends up being minus 0. Notice that this quantity right here is in fact the area underneath the curve. It has two terms. There's one term that's associated with a triangle up here, and there's another term that's associated with a rectangle down here, like so. That's the left-hand side of the expression here. However, this quantity here, the area underneath the curve, is also the same thing as the change in position. Once again, this is a reverse process of differentiation. If the derivative of position with respect to time is velocity, then the integral of velocity is equal to the position. That's what we've shown here. And then the last step in terms of deriving the expression is to move the x naught to the other side. Like so, and there's the second of our two kinematics equations. So strictly speaking, you then examine motion mathematically by using derivatives and by using integrals. I have two mathematical examples for us to look at now involving non-constant acceleration. We'll look at those examples in part 4, the last part of this lecture.